Good afternoon. Now we'll begin with the first lecture on remote sensing overview and Earth observation data for urban planning. Let me begin with in the field of urban planning, we have got several innovative technologies, and these technologies are helping us for the mapping, monitoring, and management of urban areas. And some of these technologies are remote sensing, photogrammetry, LiDAR, geographical information system, global positioning system, UAV, GPR, and so on and so forth. As of now, in the field of remote sensing, we have got variety of data sets available from the aerial and space-based platform. We have got variety of resolution data available. They are available from the IRS Indian Remote Sensing Satellite Series or from data from the foreign origin. We got the opportunity to utilize these data sets using the photogrammetric techniques, and these accordingly based on the platform from which the data has been acquired, we can process the data using the either the aerial photogrammetry methods, aerial photogrammetry, or the digital photogrammetry methods, or the close range photogrammetry. The LiDAR, though the opportunity is coming up, but we have got the data from the terrestrial laser scanner. We have got the data from the space-based LiDAR systems, but they have got limited opportunity because of the very poor footprints. All these data can be processed, they can be assimilated, georeferenced, and integration and analysis is feasible. The global positioning system facilitates the georeferencing of the satellite data of varying resolution and also for the assets mapping. We know the coming of field is the UAV, unmanned aerial vehicle, which is helping us mapping of urban areas. GPR, as we understand, this has been used being used in the several field of urban planning for the utilities mapping. Now all this data we have got, the technology is coming up. Now let me begin with the definition of the remote sensing. As we all know, remote sensing is the science and art of obtaining information about an object, area, or phenomenon through the analysis of data acquired by a device that is not in contact. We have got several definitions available in the text, but basically all these definitions, this speaks about information acquisition about any feature on the surface features through variety of methods. These remote sensing invariably require are the source of illumination, and which will be sensing the features from the target. The based on electromagnetic radiation principle, the reflected, emitted, or the backscattered energy will be recorded by the sensor. This sensor back again will transmit the data back to the data recording center on the earth, and this data will be finally transformed into some utilizable product. Now let me go through some brief history of remote sensing. There are several milestones in the history of remote sensing. We had a very important milestone when the aerial photography was conducted using the aircraft. Later on, this has happened, and we all know the Wilbur Wright brothers, they have conducted this experiment. Subsequently, during the 1950s, the remote sensing word was coined by the Evelyn Pruitt in mid-50s. And there's a major milestone happened, the ERTS. Landsat, later rechristened as Landsat satellite, was launched during 1972. Subsequently, we have seen the advancements in the computer technology, hardware, software. They have seen several fold increase in their processing and also the data analysis procedures. And this all has led to the subsequently the changes, advancements in the digital image processing. And we had a very important milestone when the Indian remote sensing satellite, first IRS-1A with two important camera, LIS-1 and LIS-2, was launched in 1988. Now let us go through the remote sensing process as briefly explained in the previous slide. We invariably require a source of illumination. which is a part of passive remote sensing. We can also substitute the source of illumination with the active remote sensing. Now this remote sensing, when energy falls on the Earth's surface features as explained earlier, the reflected, emitted or the backscattered energy is recorded by the satellite. Satellite in turn will transmit the data to ground receiving station. This ground receiving station will transmit the data to the data archival system, where the data products will be generated, which will be later on given to the user for the interpretation and analysis, and finally some utilizable product will be generated at the user end. So we have got the components from the source of energy, finally some kind of utility product is generated. Now as seen in the previous slide, we require some kind of energy source or illumination to target, to which can illuminate the target of interest. Now when the energy moves from the source to the Earth's surface, it passes through the atmosphere. So it will come in contact with the atmosphere, and this will take us, when it is from the transmitted energy, reflected, emitted or backscattered energy, after interaction with the Earth's surface material, it goes from the target again back to the sensor. Now during this process, some kind of atmosphere and the energy interaction takes place. Now we have got, after the energy is transmitted, the signal which is recorded by the satellite, and then this signal is transmitted back to the ground receiving station. Now this energy, when it happens, the interaction with the target happens. So it interacts with the target depending on the properties of both the target and the radiation. So this radiation, it is scattered or emitted based on the material property and also the geometry of the surface features. Now once this energy, this data is received with the ground receiving station, it is sent to the ground archival system, and later, as told earlier, it is a useful product is generated and is given to the user for interpretation and analysis. Now this, during the process of transmission, reception and processing, often which is done in the electronic form in the recent times, the receiving the processing station where the data is processed, it is normally given to the user in the form of image. Now image will be supplied to the user either in the hard copy or the digital form. But the time has matured where we are getting more used to the digital form. We at our place, normally we all understand the Google Earth and also the Bhuvan images. And these images, they are all interpretation and analysis is done, and the derived product is given to the outside community for information extraction and for further use. Now finally the output product is generated. Now let us understand the further remote sensing technology. Now the remote sensing, the sensor is mounted on a platform, and this platform is on board the satellite. Now the platform will be, either it may be the ground based platform or airborne platform or the space-bound platform. So basically three kind of platforms are there, and this platform will be, when it is on the ground, it will be close to 1 meter, or when it is in the space, it may go to up to the 36,000 kilometer height, where normally the geostationary satellites, they are placed in orbit. Now let us understand the orbit. Basically the orbits are of two types. First is the geostationary orbit. Second is the polar orbiting or the sun synchronous orbit satellites. So the geostationary satellites, it is nothing but an equatorial west to east satellite orbiting the Earth at an altitude of 36,000 km. It is the altitude at which one revolution in 24 hours synchronous with the Earth rotation is normally made, and normally this kind of platform is used for the communication and meteorological applications. And some of the satellites which are placed in the geostationary satellites are GOES, Meteosat, Intelsat, INSAT, and so on and so forth. In the sun synchronous satellite, it is normally used for the remote sensing satellite, in which the orbiter plane is near polar and the altitude is such that satellite passes over all places on Earth having the same latitude twice in each orbit at the same local time. And we have got several of the satellites working the remote sensing which are sun synchronous. For example, Landsat, Spot, IRIS series, Nova, CSAT, TIROS, so and so forth. And where the IRS stands for Indian Remote Sensing Satellite Series. Now, as explained earlier, the remote sensing can happen whether the passive or the active. When it is passive, it uses the energy provided by the sun and the earth. And we have got the platform either the aerial or the space based. Now, this passive remote sensing is all used for earth resource mapping and the monitoring. Some systems are active, for example, radar, LiDAR, sonar. LiDAR means radio detection and ranging. LiDAR, light detection and ranging. Sonar, sound navigation and ranging. This is normally used for the altimetry and imaging. And normally the microwave satellites, they also have got the active sensors. Now let us go through some of the, we all know that there are some certain advantages with the remote sensing technology. First of all, it has got the global coverage. It has got the synoptic view. Synoptic view means we can see a large area in a single shot at one place. Unlike when you are visiting and sitting somewhere on the ground, you have got a limited view. So remote sensing offers the synoptic view. Repeatability, it has got a repeatability advantage. Same area based on the satellite characteristics is revisited. So it offers advantage in the terms of urban mapping. It offers you see the same place at different times and you are able to see the urban sprawl and growth. So it has remote sensing is also got the advantage of cost because it from the varying resolution the cost may be varying close to something like 2 paisa per square kilometer to it may go up to something like close to 500 rupees per square kilometer depending on the choice of resolution utilized. Now, remote sensing, like any technology, has got some limitations. Now, remote sensing limitations are because it uses some the instruments, and like any instrument, this also needs some calibration. Because as we have seen in the previous slide, it normally records the reflected, emitted, or backscatter energy. This energy from the source to the target, again back to the source when it comes, it also causes some kind of systematic and non-systematic errors, which we will understand in the subsequent lectures. So these kind of errors which are creeps into the data due to the either because of the sensor or due to the acquisition mechanism, it needs correction. When utilizing the remote sensing data, we require some kind of knowledge or the skill of the interpreter. And also any kind of measurement when you're doing, it has got some kind of uncertainty, and these uncertainty will be known or unknown, and it may all lead to some kind of accuracy because any kind of measurement has got the inherent accuracy characteristic. So these all error, whether it is a human or the process induced, needs some kind of correction. Now let us go further, try to understand from the urban planning point of view, because often the people in the urban planning fraternity, they always need what kind of data should I use, what kind of resolution should I use. Suppose this particular kind of plan is to be prepared, what kind of data is required. So the resolution in that context is very, very important. Basically, the resolution is ability to distinguish objects which are spatially near or spectrally similar. We often specify the resolution in terms of linear size of smallest feature that we can discriminate. Often the resolution is expressed in meters. Now the remote sensors measure differences or variations of objects that are often described in terms of four main resolution. And each of these resolution, it affects the accuracy and usefulness of remote sensors for urban mapping. Now these all resolutions are basically spatial, spectral, radiometric and temporal. In the subsequent slide, we'll try to understand what these kind of resolution is going to affect the processes in the urban mapping. Now let us go into the spatial resolution. Normally, we are all used to the Google images and also the upcoming high resolution images in the Bhuvan data sets. Bhuvan is the Indian remote sensing data portal. We have got the variety of Indian remote sensing data and also we have got the variety of other thematic data sets which have planned during various missions. Within the Bhuvan, we have also got the data set which is prepared under the National Urban Information System that we will see in the subsequent slide. Now, the spatial resolution is always desirable in the context of urban mapping because as we go further, I mean, because normally the building and the footprints they are seen in the higher spatial resolution, and that is why the higher spatial resolution is desirable as the built-in features are comparatively small in size. Now, whenever we going for the mapping, a minimum of 4 pixels within object is required because the mapping when you are doing it, the minimum mapping unit plays its role. Because we are going with the in the context of mapping, not we the various elements of image interpretation. For example, shape, size, texture, orientation, pattern, shadow, and association comes into picture. So we should understand the various aspects of the image interpretation. This we will discuss in the subsequent lectures. Now often the question arises, it's land use versus land cover, because land use is the utilization of a particular piece of land by the human beings, and the land cover manifests the natural cover or the cover which is present on the earth surface. So we have to understand these two things when you are talking about the spatial resolution, and corresponding to the requirement we have to choose the spatial resolution. Now let us come to the spectral resolution. We understand the spectral is nothing but the number of bands. So we have got, because more number of bands means our spectral distinction between the feature becomes better. In that context, when the number of bands are more than one, it constitutes multispectral data, which enhances ability to distinguish features, but we require further interpretations skill to distinguish between the various urban features. In the context of a spectral resolution, we have got the panchromatic data where one single band data is there, multispectral where more than one bands are available. We have got the high spectral data where the hundreds of bands are available. In the context of characteristic and so on and so forth. Now the radiometric resolution is also very important, because the higher the radiometric resolution, better the capability to distinguish between the features and aids to the interpretation. Now Indian remote sensing satellite systems have got a variety of remote resolution available, but the point to be made here that there is a catch. There is a catch in the sense, like higher the spatial resolution, the inferior the repeativity, and also inferior the data availability. I mean, that way the spatial spectrotemporal radiometric resolution. So for example, let us take a very coarse resolution where the data is of 1 kilometer from the INSAT series, where we have got the 30 minute, every 30 minute the imaging is done, but because the data is very coarse, we are able to map it at close to 1 million scale, and this is useful for the climate and weather only. But let us, when you go for the higher spatial resolution to the extent of 360 meter, where the every 2-day imaging is feasible, and which can help us in the 1:25000 scale mapping, which has got relevance in the ocean application. Move further, we have got data of 188 meter from the WIFS, where the every 5-day imaging is feasible and which is useful for the 1:250 scale mapping. This can help us in national surveys. Move further, when you have got the data of 23 meter from the list 3 sensor, where the every 22 days imaging is feasible, this can help us in 1:50,000 scale mapping, and this is helpful for regional analysis in the context of urban and regional mapping. We have got the data of 5.8 meter from the LISFO sensor where the every 5-day imaging is feasible, and this can help us in 1 is to 12,500 scale mapping. This is good for large scale mapping, and also we have got the stereo capability. 2.5 meter and also the 1 meter data which can go lead to the in the context of our urban mapping, we can go up to the zonal plans or better mapping. So variety of remote sensing data for in the spatial, spectral and temporal and the radiometric resolution domain, they are available. They are working in the optical or microwave regions. Now let us try to understand each kind of resolution. Now the spatial resolution, it refers to the size of smallest object that can be resolved on the ground. Now the spatial resolution is normally put into three categories: high spatial resolution, medium spatial resolution, low spatial resolution. Normally the high spatial resolution is, normally it varies from 0.6 meter to 4 meter. We have got variety of data of Indian or the foreign origin. For example, the Cartosat 1, Cartosat 2, we have got the data of elsewhere from GeoEye, WorldView 1, WorldView 2, so and so forth. From the medium spatial resolution, we have got the data which varies from 4 meter to 30 meter. We have got data from sources like Aster, Landsat, Risosat, so and so forth. We have got data from 8 low spatial resolution where the resolution will vary from 30 meter to 1 kilometer nearly, and it will be available from CVIX, GOES, AVIX, OceanSat, OCM, so and so forth. Now subsequent slide will show you, and there is an elaborate list is available elsewhere. We have got the variety of sensor satellites which offer data in the category of high resolution satellite. For example, Cartosat 1 offers the data of 2.5 meter, Cartosat 2 of the close to 1 meter, IRS-1C 1D close to 5.8 meter. We got satellites from Pleiades where it is close to 0.5 meter, and then Spot. Then we have got ComSat, WorldView, GeoEye, ALOS, ComSat, QuickBird, so and so forth. In the some medium resolution satellites are available. For example, Landsat, IRS-1C and 1D, Landsat, then we have got Spot, then we have got CBR, so and so, and then other satellites where number of bands, spatial resolution and the revisit capability, they are all mentioned in this one. And the where the spatial resolution varies from 10 meter to the 30 meter, and the spatial resolution it also varies. In the terms of low resolution satellite data, we have got examples from Meteosat, Nova and so forth, which offer resolution close from 200 meters to the 2.5 kilometer, where the swath where in one single coverage they have got the panoramic swath to the extent of 3000 kilometer to the half of the earth can be visualized in a single frame. Now let us try to understand the spectral resolution. As explained earlier, the spectral resolution is put into three categories. It is panchromatic, multispectral or hyperspectral. Panchromatic, it contains normally single band black and white image which normally works in the 0.4 to 0.7 micrometer in the visible range. And on the right hand side we have got one typical image of the panchromatic, black and white. Now this has got some limitation. We can see the features, but because the color is not present, and the color comes when you got the multispectral phenomena. Because the color is not present, though the features can be seen in the higher spatial resolution category, but the spectral phenomena aids in feature distinction better. But the multispectral image, they have got several discrete bands, and the width of these bands, this all varies, and several examples are available. For example, we have got one multispectral band available on the right hand side of this slide, which consists of 4 bands, and these bands are blue, green, red and infrared. We also got some examples from the Indian remote sensing satellite series. Then we have got the multispectral, hyperspectral images where we have got the 100 or more continuous spectral bands, and which helps in based on material properties. Particular phenomena can be studied in detail. And the example, one typical example is the NASA's EU-1 satellite, and we all know about the Hyperion. Now, when you talk about the spectral domain, we have got wide variety of electromagnetic spectrum. Normally, we are used to mapping in the optical, but subsequently, the technology is advanced, enhanced, and then we have got the data from the hyperspectral, thermal bands and beyond. Now, in the optical, when you take it 0.5 to zero point 0.7, we have got several discrete bands available. In the thermal, also based on the atmospheric window available, we have got the data sets available. In the microwave, also based on the different frequency, in different frequency domain, the satellite bands are available. Now, this particular slide shows the spectral reflectance curve. Now, the spectral reflectance curve, it helps us in understanding the material and energy interaction phenomena. For example, in this particular slide, which is general, it has been general in nature, it shows the material and energy interaction for three kind of features, and most prominent is the vegetation. Now you see one curve which shows the signals outputs generated when the energy falls on the surface and recorded by the satellite. You see there is a sharp spurt in the infrared region. Subsequently, we have got a dip, and then after the dip, the signal intensity goes down, and then we have got several spikes and then rising phenomena. This is about the vegetation characteristics. When we talk about the water, normally the water based on the content of turbidity and the depth. Again, the energy matter interaction varies, and the signal strength increases when it goes to the blue, and finally as it touches beyond red and beyond, the signal strength goes minimal. Concrete or the urban development, normally this all bright in various spectral bands, and there is a gradual dip is there as the wavelength increases. Now this is a typical high resolution image which is for one urban area where you are able to, because this is a multispectral image, and also this is the natural color composite which has been generated through some computer digital image processing based algorithm. Now you are able to see a typical phenomena which is there in an urban environment where the buildings are there, vegetation is there, and these all buildings will fall in various categories which we'll try to understand in the subsequent lectures. Now there's one more domain as explained earlier, that's the hyperspectral remote sensing, because when the technology is maturing, the need is also felt about the pure signatures. Now the purity comes when the bandwidth is narrower. Now this narrow band means 5 to 10 meters. When this kind of data set is being used, we are able to distinguish between the various urban material, whether it's a brick, concrete roof, road surface, bare soil and sand. But as of now, because the data of high spatial resolution in the hyperspectral domain is not available. So there is very limited opportunity available from the space-based platform. But we have got data from the aerial platforms which can help us in understanding the Earth surface features. Next, the important resolution is the radiometric resolution. The radiometric resolution helps us to understand the features which may look similar when the radiometric resolution is coarser. When the radiometric resolution is finer, it may be we are able to distinguish between the features. So it is the nothing but radiometric resolution is the smallest change in intensity level that can be detected by sensing systems. It is nothing but quantization is a technique of representing the radiometric levels by the limited sets of numbers available. For example, if a sensor of 8-bit is used to record the data, there will be 256 digital values available which may range from 0 to 255. Now this all one typical example of radiometric resolution. When you got now you see how the information content varies when it is 8 bit and when it is 1 bit. You see when it is 1 bit it is either black and white. When it is 8 bit, 6 bit, 4 bit, 3 bit or 2 bits, that means 4 level to the 256 levels, and the information contents increases. And you see that in the urban areas, because the features which may look only, suppose you got the 1 bit data, you may able to see maybe the urban and non-urban features only. But within the, to make the distinction between the within the urban features, quantization level can help us. Now the fourth important resolution is the temporal resolution. Now this temporal resolution is nothing but the repeativity of the satellite to image the same area at different time period. Now the temporal resolution has got very distinct advantage in the field of urban planning because we are able to find out the multi-temporal phenomena. For example, urban sprawl. We can also see the floods happening in the urban areas or several other phenomena which are occurring also in the non-urban areas. Now, often what may happen that the image is being acquired that may be of under the cloud. Now, when the temporal phenomena is there, we can find out the alternate date where the cloud-free data of the Earth's surface can be obtained. Now, the temporal resolution also generally increases. This one important point is there that the temporal resolution generally increases higher latitude due to the significant side lag between the consecutive satellite passes. The two different terms I want to make the distinction at this point. There is a repeat cycle, there is a revisit time. Both they all constitute subdomain of the temporal resolution. Repeat cycle is the time in days between two successive identical orbits, which is normally happens. But because of some exigency, the sensor is tilted and that help us in minimizing the revisit time is the time between the two subsequent images of same area, which is the property of pointing capability of the sensor. Now, this is one typical example from the aerial remote sensing, how the stages of development in the urban area that can be visualized, where the node development is there and finally a settlement has come up, and that is, and the phases of development can be seen using the temporal remote sensing data. Often the question arises the mapping scale versus resolution. You see on the right hand side we have seen one pyramid here. Normally the spatial resolution is also a function of the latitude. Higher the latitude, there will be overlaps will be there and the resolution goes coarser. And normally the map scale is a function of pixel ground size and the pixel density. Basically, resolution is a function of latitude, zoom level and a constant. And scale is dependent on, because after all you are going to generate the product on the screen as a as a digital data, or you are going to print it. Now, when you are going to print it, it becomes a function of dot per inches. So basically one has to find out relationship between the mapping scale versus resolution, and which is expressed mathematically as 1 upon pixel ground size into pixel density. So that the 1 meter on the map represents so much x meter on the ground. Now let us go further in the requirements of the urban planning. Now typically in the context of urban planning, urban planners, they deal about various kind of plans, starting from site plan to the zonal plan to the district plan to the perspective plan or the regional plans. So this way, and these all plan from, they are varying from to something like close to 2000 to 4000 to the something like close to the 50,000 or higher. So accordingly, one has to find out the appropriateness of the spatial resolution, spectral resolution, temporal and radiometric resolution characteristics, and accordingly the applications can be derived. Basically, the choice of resolution depends on what one is looking for and accordingly the matching kind of data sets has to be chosen. For example, when suppose somebody is looking for the macro level regional perspective plan, which this resolution of something like 80 to 360 meter is sufficient, where the mapping scale is something like close to 1 is to 50,000 to the 1 million, and several applications are feasible we can see, but there are some limitations. For example, urban sprawl, urban land use at one level 1, or we can go to the infrastructure planning at broad level. When you come to the micro level planning, where the high resolution satellite data 0.6 to 4 meters required, then you require the scale of 1 is to 1000 to the 5000, and there high resolution satellite data can be used for urban land use mapping to the level of 4, and we go to the further down in the line into the urban mapping, we can see the slums or mapping of street level urban road network or the property parcels or the infrastructure development, utilities and services maps or the population estimation. In the infrastructure planning, we can go for the six site project site analysis, so and so forth. In the disaster, we can see the specific whether particular building is got damaged or not. In the rural development planning, we can go to the particular the cadastral level land use land cover maps, land parcel, so and so forth. In between, we have got the MESI level planning, which may require the medium resolution satellite data, 4 meter to 30 meter, and the scale corresponding scale may vary from 1 is to 10,000 to 1 is to 50,000, and we can go up to the level 2 of the urban land use land mapping, and we can also go for the several kind of urban planning exercise, for example the urban suitability analysis and so forth. So basically the message here is the based on the objective one has to choose the data, satellite data of the respective spatial, spectral and temporal resolution. Now we have got, because the remote sensing utilization has been well understood in the field of urban planning, accordingly in the year of 2006, under the project called National Urban Information System was launched with a large scale urban geospatial database for various levels of urban planning, infrastructure development and e-governance have been devised, and total 152 towns have been covered in the phase 1, and now it is coming up. Now this kind of database is going to be helpful, immensely helpful to the urban local bodies for the urban planning, infrastructure development or e-governance, and this database on the Bhuvan NUIS portal. Now this NUIS database contains total of 16 layers. These layers consist of 12 primary layer and 4 incorporated layer. 12 primary layers are urban land use, physiography, geomorphology, structures, lithology, soil, drainage, surface water bodies, road, rail, canal, transport nodes. In the incorporated layers, we have administrative boundaries, forest boundary, settlement and village locations, city, town and other boundaries. And these all covering the all 6 levels of the type of cities, ranging from class 1 to class 6, and also the cities. Total 152 towns have been covered under the NUIS program, and this data is available on the Bhuvan NUIS platform. Bhuvan NUIS platform also now contains the data of 1 meter resolution, and as of now, as on today, 313 cities, data of 1 meter has been hosted on the Bhuvan NUIS. And this is the typical data which is available on the Bhuvan NUIS. This data is of 1 meter resolution. You see the typical area of parts of Delhi, which is very well seen in the satellite data. Now another question which arises in the context of urban planning for various kind of details. The point which I want to make here, that the level of details is also a function of resolution, type of plan being made. For example, when we talk about the perspective plan, we do not go in detail. In the context of perspective plan, which is very coarse in scale, which may go 50,000 or coarser scale, probably the built up area will limited as a single class unit, that is a level 1. When you go further in the development planning, that means the scale of mapping increases, the information content increases, the built up area will be further subcategorized into rural, residential, industrial, commercial or recreational. When you go to the zonal planning, that means 4000 scale or better, here the same residential area is further subdivided into high rise, medium rise, low rise, slum or other categories. Further, when you go for the project or specific site plan or kind of category, then this all built up area will be further subcategorized into apartments, apartment flats and row houses and tenements. So this way, as you move further, accordingly information contents increases, level of details increases, but please mind it here that you also require corresponding matching kind of satellite data. When you move further, when you go further in the public and semi-public, for example, where the categories are further subdivided into health, education, religious, public utilities. Accordingly, in the fourth category, information content will further increase. So again, I want to reiterate here. So as you move further, the information content when it is increasing, so you have to match with the spatial or spectral resolution. For example, in the next category, built up land, we have got the transport and communication, or in the further in the mixed built up land, slum areas, vacant land, culture and so on and so forth, where the information content is subsequently increasing. Again, one has to keep in mind the requirement. Now with this, I conclude here, but I want to again emphasize here that often the processes in the urban planning field, they are multidisciplinary in nature. So one has to keep in mind the project requirement. Accordingly, one has to choose the matching kind of satellite data of spatial, spectral or temporal resolution, and accordingly the project has to be framed up. Thank you.